Hey everyone, this is Dr. Walker. This is video 259, magnetic force between two current carrying wires. This video kind of puts together a couple of the topics we've been talking about, such as magnetic force on a wire and magnetic field due to a wire. Let's take a look at the concept here. If you have two wires carrying current, why is there a force between them? So the first idea is that if you just look at one of these wires, that one wire produces a magnetic field as shown. This comes from right-hand rule number 2, where we have the thumb pointing in the direction of the straight current. Remember, straight thumb, straight current. And then the fingers looping in the direction of the field. So to the left, they're coming out of the page. To the right, they're going into the page. So that's the magnetic field loops that we can represent as dots out of the page on the left and X's into the page on the right. Okay, now what we're going to do is we're going to put a second wire in the location of the magnetic field produced by the first wire. So we know that we have a magnetic field into the page here produced by wire number 1. So we don't care about wire number 1 anymore. We just care about the fact that it produced this magnetic field into the page. Now, what is the direction of the force on wire number 2 now that it is in this magnetic field into the page? Do you remember which right-hand rule that is? That's right-hand rule number 1, where you point your fingers in the direction of the current, you fold in the direction of the field, and the thumb is the direction of the force. So let's take a look. We point our fingers straight up in the direction of the current. We fold into the page, so away from you, the direction of the magnetic field. The thumb points in the direction of the force. So the force is to the left. So there we go. We have two wires that each have a current. Because each wire produces a magnetic field, the other wire finds itself within that magnetic field and thus experiences a force. We do have an equation for the force between two wires, and the equation is that the force per length equals mu naught I1 I2 over 2 pi d. And this comes simply from the fact that the magnetic field produced by one wire is given by mu I over 2 pi r. And so let's have the distance be d. So let's pretend this is a d here. D is the distance between the two wires. So let's say that this is field 1 here produced. Well, actually, this picture shows field number 2. So let's say that this is field number 2 here, produced by current number 2. So at the location of wire number 1, that's a distance d. So we can change the r to a d. At the location of wire 1, how much field does wire 2 produce? Wire 2 produces this much field at the location of wire number 1. So how much force does wire number 1 experience? F equals ILB sine theta. And theta is 90, so this is going to be 1. Theta is 90 because the field here is out of the page, the current is to the right, so the field and the current are perpendicular to each other. So this is the force that wire 1 experiences. It's equal to ILB, where I is the current of wire number 1, L is its length, and B was the field produced by number 2. So you can see kind of where this comes from. 2 pi d. This equation here is the exact same equation that's over here, except we have divided both sides by L. Notice that it doesn't matter if it's F1 or F2, because Newton's third law tells us that the forces are the same. If wire 2 exerts a force on wire 1, then wire 1 exerts that same force, but in the opposite direction on wire number 2. The reason I like to go through this derivation, because you know that I don't usually go through derivations, is because I feel like it's really important to understand that one wire is producing the field, that other wire finds itself in this external magnetic field, and that's why that other wire experiences a force. Okay, with that said, let's take a look at this question here. It says two parallel wires carrying currents in the same direction. Do they attract or repel each other? We know that they're going to affect each other because the wires will experience a force. So, how can you do this? Well, we've already done half of this in the previous page here. We saw, a couple pages ago, we had two wires going up, and the current going up, and the force on wire number 2 was to the left. So we know that the force on wire number 1 has to be to the right, right? Newton's third law. So without doing any work, we can see that when the currents are in the same directions, the wires will attract each other. Now, what we could do is we could just go through the same process, and I do think that it's a good exercise. So we can do that real quick. We already know that this wire here experiences a force to the left. So let's do the same process and see what kind of force the left wire experiences. First, we need to know what is the field here. The field is produced by wire number 2. Put your thumb up, curl your fingers in the direction of the field, and you can see that to the left of the wire, your finger should be pointing towards you, out of the page. So wire number 2 is producing a field out of the page everywhere to the left of that wire. So now bring in wire number 1. Wire number 1 finds itself in a field going out of the page. So use right hand rule number 1 to find a force on the wire number 1. Point your fingers up and see over here. Fold in the direction of the field, which is out of the page, so towards you. And the thumb is to the right. So the force is to the right. So it's just the same process, but to see that two wires carrying current in the same direction will attract each other. So to summarize, this slide, two wires carrying current in the same direction will attract each other, but two wires carrying current in the opposite directions will repel each other. So I encourage you to go through the process that we just went through to really see that the forces are in the direction shown and that they do repel each other. I'll leave that as an exercise for you. And lastly, let's do an example. Jumper cables. Those are two wires, and they carry currents in opposite directions. So that means that they experience a force. So why don't they fly apart? Well, I mean, they are tied up together, and that force is not going to be super strong, as we're going to see in this example. So in this example, we have the length of the wires. So, oh no, that's the distance between the wires, sorry. So D, and let's convert that to meters, 0.012 meters. That's the distance between the wires. And then we have the length of the wires is 3.7 meters, 3.7. And then we have the current is 150 amps. And we want to know what's the force between the wires. So it's a plug and chug. The equation we just saw was F over L equals mu I1, I2, and it had also over 2 pi d. Just double checking, don't want to make a mistake. So if we're looking for the force between the two wires, we're looking for F. So what we do want to do is we want to multiply both sides by L. Multiply by L so that we can get the force by itself. So then we just plug and chug. Mu is 4 pi times 10 to the negative 7. I1 is 150 amps. I2 is also 150 amps. They carry the same current. L is 3.7. And then divided by 2 pi. Then the distance between the wires, 0.012. Plug all of this in the calculator. The pi's do cancel out, so you don't have to put them in. And the answer that we have here All of this ends up being 1.4 newtons. So not a super strong force, but there definitely is a force between two wires, whether they carry that current in the same direction or in the opposite direction. That's all, folks. I hope you enjoyed this video. I'll see you next time.